Hello friends, welcome to my this DSA series with Java. So in this video, welcome, and I'm going to talk about big O notation, what, why, and how. So we have learned something about the time complexity in the previous video. If you have not watched that video, please kindly I request you to watch those videos, time complexity and space complexity. Now in this video we're going to talk about big O of notation. Okay, so let's get started here. The big O of notation in detail here. The goal of this video is to understand what is big O of notation or big O really means, and to analyze a simple code to know which solution is better and why. So this is a very important video from interview point of view. So don't miss, and from logical thinking point of view, it's very important video. Don't skip this video. Watch till the end. What is a big O of notation? So big O of notation tells us how performance grows as the input grows. So that is basically it's telling how performance grows if the input as the input grows. So it ignores the machine speed and the programming language. So these two things are not taken into the consideration. Machine speed is not considered. Programming language is also not considered. It focuses only on the growth rate. Okay. So real life analogy, if I want to relate it, is if there is one person cooking versus 100% 100% cooking the meal. So there is a difference there. Cooking for one person or cooking versus cooking for 1,000 or 100 people. Okay, so there is a difference there. Now, why big O of notation is important? This thing is that it helps us to choose a better algorithm. It is used in interviews, makes the code scalable. So you can scale the code as a very efficient in an efficient manner. So example is your on your screen that if n equal to 10, the difference is small. But if n equal to 10 lakh, the difference is huge. Okay. So it depends upon the input now. So rule for big O of notation. Okay. This is the most important part. Please listen this carefully. So examples I have here. Rule 1. First rule is to drop the constants. If you have a constant, let's say if you have this O of 2n, so if you drop that constant, your big of notation becomes O of n. So basically you're dropping that constant, so it becomes O of n. And again, if you have O of 100, if you drop the constant, it becomes the O of 1. So this is the first rule. Now the second rule is drop the lower order terms. So if you have big O of notation as O of n square plus n, then drop the lower term, that is the n. If you drop that, it becomes O of n square. So this is a rule 2. Rule 2, you have to drop the lower order terms. Then you have a rule 3, different input, different variables. For different input, you need to take a different variables. So let's assume you have array 1, you are giving as n, and you have array 2, you are giving it as n m. So if you want to calculate the time, that is equal to O of n plus n. Now that is being added here, n plus n. Okay. Now big O of notation with the loops. Okay. If you have a single loop, then it is O of n. If you have nested loop, then big O of notation is O of n square. And loop with half input. Okay. So for that, the big O of notation is O of log n. O of log n. Now let's come to the first case, that is a single loop. that is O of n. Now suppose you have a loop that runs from 1 to n. So I have taken the example here for int I equal to 1, I is less than n, I plus plus. Some constant work this loop is doing. If you have n equal to 5, the loop runs 5 times. If you have n equal to 100, then the loop runs 100 times. If n increases, then the operation increases linearly. So if your n is going to increase, the operation is going to increase linearly. Okay. Now, the number of operations grow directly with the input size. So it's directly growing with your input size. Now the final conclusion is that the time complexity, that is equal to O big O of notation, that is equal to O of n. Okay. Now let's relate to this analogy. It's basically checking. Analogy is here is checking every student's attendance in a class. More student, more time is required, right? If you're checking the attendance, if there are lot number of many students in the class, you will require lot many of time. Okay. Now next is the nested loop, and for that big of notation is O of n square. Now imagine a loop inside another loop, both running n times. Okay, so outer loop runs n times. For each outer loop, the inner loop runs n times. Okay, so total number of operation would be there n into n, because both the loops are running n times. So that would be multiplication. So that is n into n. Now here you have a nested loop here. You have outer for loop, you have inner for loop. Outer for loop starts with I equal to 1, I is less than n, I plus plus. And lower loop, inner loop starts with the int j equal to 1, j is less than n, j plus plus. So both the loops are running n times here. So that is, you are getting the time complexity as O of n square here. Now some more thing about the nested loops. If you have n equal to 3, the number of operations would be 3 into 3. That is 9 operations. If you have n equal to 10, the number of operations would be 10 into 10. That is 100 operations. For every single iteration, we are doing n more operations, right? So for every single iteration, we are going to do n more operations here. Final conclusion is that the time complexity, that is equal to big O of n square. Now if we are going to compare this analogy, comparing every student with every other student. So that is something like that. If you are comparing every student with every other students, right? Now the next is loop that has input. For that, big O of notation is O of log n. So you have a, if you have a loop, while loop, you can see if n is greater than 1, then you have n equal to n by 2. So what you are doing is, you are every time uh, decrementing the value, dividing the value, right, by n by 2. So for this kind of loops, you have a complexity, that is big O of notation as O of log n. So here you are, instead of increasing or decreasing by 1, the input size is reduced to half each time, right? Because you're dividing by 2. So every time the input size is reduced to half. So explanation is like, if you have n equal to 16, then the steps are 16 would be divided by 2, then 8 comes, then after that 4 comes, then after that it is divided 4 divided by 2, the 2 comes, and 2 divided by 2, the 1 comes. So total number of steps you require here is 4 steps. Even n becomes very large, let's assume n becomes 10 lakh, still the number of steps, still you have number of steps very small. Okay, that is very advantageous for this kind of thing. When the input is divided every time, every divided by 2 every time, the growth is logarithmic. So whenever your input is divided every time by 2, your growth is logarithmic. And the final conclusion is that the time complexity is O of log n. Analogies like this, if you want to relate it, is that searching a word into a dictionary by opening the middle page each time, right? So every time you are searching a word into a dictionary, opening a middle page. So that is every time you are reducing the dividing the input by 2. So it's getting lesser and lesser. So for this kind of the thing scenario, you have a time complexity is big O of log n. Now, comparison summary here is single loops grow linearly, right? For that, the complexity is big of notation O of n, and nested loops grow very fast. For this, the big O of notation is, that is time complexity is O of n square, and for halving loops grow very slowly. For this, the notation is big O of log n. If you like this DSA quality content, kindly like, share, and subscribe this video. Thanks for watching this video. Thank you.